Welcome to a lesson with Dr. Powell. Let's consider the relationship between series and integrals if they can be compared. Let's first discuss when they might be comparable. First of all, when we have a series, we're adding terms and we're adding terms all the way forever to infinity. We're going to be thinking about integrals that go off to infinity as well. And this may start in any number of places, and this is also going to have a place that it'll start. And we want to compare the two, so that's kind of what we'll be looking at. Something else that we need is to realize in this comparison that we are going to only be thinking about comparing things when we have terms in here, but when we're only assuming that these terms are positive, and if they're not, take absolute values. And the function in here is also going to be a positive function, greater than or equal to 0. So positive in both cases. So really the question here is we're going to be considering the convergence or divergence of the series if everything is taken to be positive, and if they're not, take absolute values. So that type of convergence is called absolute convergence. The absolute doesn't mean complete or total. It just means absolute value convergence. But we usually leave that out. So maybe we should add it in. Absolute value convergence is the type of convergence we're going to be working with and thinking about as we do a comparison with a series to an integral. So the types of functions we'll consider will be ones that are positive, not ones that bounce around across the axis, but stay up here the whole time. Okay, so let's look at an example. All right. What if we have the series 1 over n squared as n goes from 2 off to infinity? Now, let's look at the graph of 1 over x squared using an x instead of an n. So this is going to be function that comes down and gets closer to this axis as we go that way. And we're starting at 2. Okay, well, at least this starts at 2. So let's think about how to picture this series here. Now, when we plug in, if we plug in different points into this function, we actually get the series, right? In fact, if we're starting at 2, the series, you can think about the series as being dots along this line. Okay, at least the y values, and you can be adding up all those y values. Now, how do you add it? Now, think about the relationship between adding up y values and taking an area. Well, especially since these y values are spaced 1 apart, it would make sense we could even say, take this y value and drop down, right? Take this y value and drop down. That's an area. That's an area. That's an area. And so we get all these rectangles. Notice that the total area underneath all these rectangles is bigger. Ooh, is bigger than the area that goes from 2 off to infinity. So if we go under the curve, so we could write that out, 2 to infinity, the area under the curve from 2 to infinity of 1 over x squared. We know that the series itself, which is the area of the rectangles, is bigger than that. Let's do another comparison here, or another thought process here. Why not instead, let's just erase these here and think about this in another way. What if we did our areas a little differently? We drew our areas going to the right. What if we drew our areas going backwards? That positions our areas underneath the curve, right? So, yeah. And the series is still the sum of all these rectangles, but now all these rectangles appear below the curve. But starting from 1, So we go backwards. So to kind of get like more area. So if we go back, we get more area. So go back and we'll be bigger than the series. So here we stayed at this point to be smaller than the series, but then we go forward, or we go backwards one to be bigger than the series. Now, also keep in mind, the only real reason why this comparison worked also was because our function was decreasing itself. So let's add that criterion. So in these comparisons between series and integrals, we're going to assume that not only are these guys positive, so the positive function, but we're going to assume that we have a decreasing function. Now, if we have a decreasing function, what does that mean? Well, if we have a decreasing function, that means that we can do this comparison because one way, all the rectangles are over. The other way, all the rectangles are below. And so hence, we have this idea. This is kind of interesting. So let's just kind of think. What would happen if, so notice that with this, assuming that this function is defined well between 1 and 2, and integral between those places definitely exists, then really the convergence and divergence of these integrals, these two integrals, just shifting between 1 and 2 is the same. If this converges, that converges. If this diverges, that diverges, and vice versa. Converge, converge, diverge, diverge, it's the same. So using that idea, we can say a lot about this series, which is sandwiched between them. So what happens if this guy converges? Well, then definitely the series will converge, especially assuming, since we're adding positive things, that everything here is bigger than 0. So if this right here is, and so we know that this series actually will, well, and also we have to think, I mean, how do we know it's actually going to converge? Well, for one thing, if we keep on adding positive things, this is actually the sequence of partial sums is actually an increasing sequence. And if that increasing sequence is bounded above by a number, right, which is bigger than the limit, then by the monotone convergence theorem, or the monotone convergence theorem, this will definitely converge and have a sum. So basically, inequality should tell us if something converges or not. If this thing right here converges, since this is bigger than this, then that'll converge. So if this has a finite area, then that has a finite area, is basically what we're saying. Finite area, then finite area. So now, what if this guy diverges? Well, then this guy will diverge. And if this guy diverges, then this guy will, because this will be bigger than an infinite area, so this one will also diverge. All right. So basically, if this converges or diverges, that means the same thing about this. Now, what about this? If the series converges, then that means that this integral actually will be ceasing finite area. And so this area is going to be less than a finite area. So it'll be finite, so it'll converge. So if this converges, that converges. Now, what if this diverges? Well, if this diverges, then this is bigger than it, so this will also diverge. So we get that we have exact equivalence of convergence divergence of this series and either this or this integral. In fact, if we want to, as we're looking at this, we could even just plain out say, I mean, just interpret this right here as an integral going from 2 to infinity and 1 over x squared, and that'll actually look at this guy. And if this guy converges or diverges, that'll say exactly about what's happening with this one. So this will only be a convergence divergence test. It's nothing more than that. It doesn't actually say what this sum is. It just says whether or not something converges or diverges. Now, it is true, you can actually use the integration to help you approximate this sum given a certain partial sum of that, and that'll be reserved for another video. But at least right here, we're going to be thinking about using just the integration in order to say whether or not this converges or diverges. So let's look at that. Well, actually, we have, thinking about improper integrals, we have a rule for um, this particular thing. So this p-value, so this is minus x to the negative p, this p-value is bigger than 1. And remember, when p is bigger than 1, we actually had convergence over here. That was part of a p rule here. So we actually know this integral converges. So we know that this series converges. Essentially, our p-test for convergence for integrals is the exact same for p-test for convergence for series. If we had a series, it looks the same, but we have an n instead of an x. So we could actually go through the computation of this integral and we'll actually see it converges. In fact, we'll just do that quickly. We take an antiderivative, that would be negative, that'd be negative x to the negative 1 or negative 1 over x. That's the antiderivative. And we're going from 2 and then taking a limit going to infinity right there. So if we take a limit of this as x approaches infinity, that'll be 0. Then we minus the negative 1/2, so we get a positive 1/2. So it looks like, so it definitely converges, just as we were mentioning with that p-test. So therefore, this series will converge. Thanks for watching.